This video will be going over section 4.4, which is graphs of logarithmic functions. We'll talk about the basic logarithmic graphs and their properties, very similar in how we did the exponential graphs section. Then the next thing, after we talk about the basic logarithmic graphs, we'll notice a couple of things that are important, are the domain and the vertical asymptote of a logarithmic function. We'll talk about how to figure those out. And then the last thing, we'll talk about how to determine the graph of a logarithmic function, which is really going to be based on the second section here. If you can figure out the domain and vertical asymptote of a logarithmic function, you really know pretty much a lot about it. I guess there is one other thing that we will notice here, and that comes from these basic graphs. Similar to the exponential graphs, we have two different pictures depending on whether the base of the log is between 0 and 1 or bigger than 1. So I'm going to go ahead and do what I did with the exponential graphs and draw each one out and talk about the important things. So the one on the left, I'll do the base between 0 and 1, y equals log base b of x. And the one on the right, y equals log base b of x. B is greater than 1. Right, so one thing that we mentioned at the very beginning of the exponential functions was there is this horizontal asymptote of x equals 0. Well, when it comes to logarithms, there are vertical asymptotes. And I will remind you, the way you figure out the inverse is you switch x and y. So if for exponential functions, we had y equals 0 as a horizontal asymptote. For logarithmic functions, we have x equals 0 is a vertical asymptote. And they will both have the same one, x equals 0. So that's something that's not different with the two pictures. Just like the exponential graphs, there's a lot of similarities. There's one key difference, which is also going to be very similar to the exponential graphs. One of the properties we talked about in the end of last section was that no matter what the base is, if you plug in x equals 1, if you have 1 inside the log, you get out 0. So on both of these, if we plug in 1, we get out 0, and we can plot a point. We have an x-intercept of 1, 0. And just like last time, the x-intercept, similar to the y-intercept of last time, is really going to just guide our picture. When you do things to the equations, it changes the x-intercept. All right, now the key difference here is pretty much the same thing as last time. If you remember exponential graphs, if b was between 0 and 1, then it was decreasing. Log works the same way. If we are between 0 and 1, it's also decreasing. And what it's decreasing, the domain is from 0 to infinity. So the graph only sits on this side. It gets really close to vertical asymptote, like we talked about with vertical asymptotes before, and it decreases, but it kind of dies off. Okay, so between 0 and 1, it's decreasing. And it decreases like this. It looks very vertical. We know towards vertical asymptotes, it never touches it. It never touches it. It goes up to infinity. That's how asymptotes work. So it never touches the x-axis, never touches the asymptote, but it goes up to infinity. All right, and one thing I'll point out, which I'll do on the calculator as well, when we just graph an example. For log graphs, when you graph them, it almost looks like the graph goes horizontal, but it goes down. It keeps going down to infinity. This one to negative infinity. It does not actually flatten out. There is no horizontal asymptote. The y value. Okay. If you turn your head sideways, so this looks like the x-axis and this looks like the y-axis, what you'll notice is the graph looks exactly like an exponential graph. It's kind of bending away from that asymptote. And that's the idea with inverse functions, is their graphs look the same if you twist your head. Now with b bigger than 1, the difference is it is an increasing graph. It's pretty much going to look like this graph flipped over the x-axis. It looks something like this. This one is increasing. Down here towards the asymptote, once again, it never touches it. It goes down to negative infinity, never touches the asymptote. And over here, it's increasing. It looks like it's going to flatten out, but it also goes up to infinity. All right, so these are the basic shapes of log graphs. They have a vertical asymptote that gets really steep somewhere, and then it just kind of dies off slowly, dies off away from it. All right, it starts leveling off, I guess you could say, is a better way to word it. All right, but the key properties here that I mentioned, the domain is 0 to infinity and the range is negative infinity to infinity. We hit on that last section as well. Right, so the range being negative infinity to infinity, it goes all the way up and all the way down for both pictures. The vertical asymptote is x equals 0. One thing I want to mention, which we'll see in the next section, is the vertical asymptote. Really what you're saying is the vertical asymptote occurs when the inside is 0. And the domain occurs when the inside of the log is greater than 0. If we do things to make the inside different, the domain changes. And then also the key difference, increasing if b is bigger than 1, decreasing if b is between 0 and 1. So just make a note of these shapes. These are what the log graphs look like. And there's only 2 topics here. One is directly related to the 2 things we just talked about, determining the domain and vertical asymptotes of a logarithmic function. And I have it outlined here exactly what you need to do. To determine the domain of a logarithmic function, we set the inside greater than, equal, and solve. To determine the vertical asymptote of a logarithmic function, we set the inside equal to 0 and solve. One thing that a couple of the homework problems do is they ask you for the range. The range of a log function is always, always, always negative infinity to infinity. At least the ones we do. You could have some sort of weird restricted domain kind of question and that won't be true, but the ones we're dealing with, it's true. Right, but you'll see once you do the domain, you need to do the domain first. You've already done the asymptote. Okay, so we want to figure out the domain and the vertical asymptote. And I forgot to take this out of the directions, but when you figure out the domain, just worry about interval notation. No need to do it the second way. Interval notation is way more important anyway. All right, so we want to do the domain first. You need to do the domain first, not the asymptote first. All right, so what we do to figure out the domain, we take the inside and set it greater than 0 and solve. We want to solve x plus 2 is greater than 0. Now when it comes to inequalities, we can add and subtract over them all we want. So just subtract the 2 to get the x by itself. And we get x is greater than -2. Now you do want to convert this into interval notation. And I talked about in the last chapter when we dealt with interval notation, you can always make a number line. So I'll do this one. You can kind of reason out the way it looks based on the inequality. But we mark off our number, which is -2. -2 is not being included. Since it's not being included, we have an open circle. And greater than means to the right. So not included and to the right. We want to be bigger than -2. Now our interval looks like this. Well, it starts at -2, but it's not included, which is a parentheses. And nothing is stopping us from going up to infinity. It's -2 to infinity. Right, now, once you've done the domain, you can do the asymptote. I'll write down what you would do, but once you've done the domain, if you figure this number out, you'll see that this is where the asymptote is. Right, so figure out the vertical asymptote, especially if you don't have to figure out the domain in a problem. If you only have to do this one, what you want to do is set the inside equal to 0. X plus 2 equals 0. And we would solve it by subtracting the 2 from each side, and we get x equals -2. But one thing to remember about the asymptotes is they are equations. You don't just use -2, you got to do x equals -2. Right, but if you do the domain and you solve it out properly like this, you're going to take the same exact steps in solving the vertical asymptote. You're always going to get that same number. So if you do the domain first, you'll actually knock out the vertical asymptote as well. The problem with doing the vertical asymptote first is it doesn't tell you which way to shade in for the domain. If you only get x equals -2, it could be to the right or the left, and you don't want to just guess that. So do the asymptote first. I'm sorry, do the domain first, get the asymptote afterwards. All right, so we got one more here just because what often happens is people always want to do the asymptote first and assume because of the greater than part, it's always going to be to the right, and that's not true. We'll figure out the domain of log of 2 minus 5x. So we take our inside, and we set it greater than 0. You can add or subtract all you want across inequalities, even with variables. So I'm going to add 5x to each side. And we get 2 is greater than 5x. And then we can divide each side by 5. Now you can also divide by numbers, multiply numbers across inequalities. The one thing I will remind you of, if you multiply or divide by a negative number, you have to flip the inequality. This is not what I did here, so I'm not going to flip it. But it's important to remember that because you may solve certain ones different ways. You might have to flip it, and if you forget, your answer is going to be wrong. So if you multiply or divide by a negative, don't forget to flip the inequality. And I guess I'll just write in here for those people that will look at this. We did not do that here. not done here. I didn't multiply or divide by a negative, just sending out a reminder. Right, but divide by 5, the 5's cancel. We do not flip the inequality. We get x is less than 2/5. If you don't like inequalities this way, you can certainly rewrite it. The x is on the narrow side of the inequality, I guess you could say, and it's opening towards the 2/5. So I definitely prefer this way. It's helpful for me. So we got x is less than 2/5, and if we want to write that in interval notation, less than means to the left of 2/5. If we're going to the left, we go all the way back to negative infinity. Right, to the left, we could go all the way back to negative infinity, and we're going to go up to, we hit 2/5. No equal part means parentheses. And the vertical asymptote, like I said, I'm not going to actually do it this time. You would just set it equal to 0, the inside. But you will get this number out. Just remember, it is x equals the number. It is not the number itself. So that is the vertical asymptote. That's the domain. As far as the inside of our logs go, we will only have what we call linear functions, meaning you won't see powers of x inside. Most of the time you deal with logs, because of the way log rules work, you don't often see powers anyway. All right, so the last thing is how to figure out the graph of a logarithmic function. From the equation, these are multiple choice. You should try to do these without your calculator, but we don't have graphing questions like the exponential section. It's not as useful, I guess you could say. There are a lot of things about exponential graphs we could dive into, but with log graphs, there's not much to them. It's just more or less using the important properties. So to graph a logarithmic function with some kind of accuracy, you want to determine the domain and vertical asymptote. Sometimes you might just need the vertical asymptote. Sometimes the domain might help. Since these are multiple choice, you might not need to do both. And then the other thing that we didn't talk about with the last couple problems is the base. We want to use the base to know whether the graph is increasing or decreasing. Right, so like I said, since it is often difficult to plot log graphs accurately by plugging in numbers or something like that, they are multiple choice. Right, but I want to do those two things. I want to look at the domain of our equation here, and I want to look at whether it's increasing or decreasing. Based on the base. If you can figure out those two things, that's really the only properties you can use to see which graph it is. All right, but it says choose the graph of y equals log base 1/4 of x plus 5. And we have these 4 choices. The domain that we just talked about, we set the inside greater than 0 and solve. We get x plus 5 is greater than 0. Subtract the 5. And we get x is greater than -5. Right, and x is greater than -5. You can also write down the vertical asymptote from here, which would be x equals 5. Remember, it matches that number, -5, not 5, the same number here. And if you look at our graphs, the two that have the vertical asymptote at -5 are these two over here. So these two have the wrong vertical asymptote. Sometimes with log graphs, the calculators don't graph the whole thing. It kind of cuts off. So this is supposed to go vertical. but both of these have the wrong vertical asymptote, wrong domain. It gets very vertical at the wrong spot. So we can get rid of those right away. Those are not, neither of those is going to be the answer. And then process of elimination, we are down to these two. You'll notice the difference. They both have the correct vertical asymptote at -5. They both have the correct domain of being to the right of -5. So we need to look at one other thing, and that's the increasing or decreasing part. Since our base is between 0 and 1, it should be decreasing. It should be decreasing, and out of these two choices, the bottom one is increasing, the top one is decreasing. But the top one is our correct answer. The bottom one is not decreasing. But if you look at those two things, you're good to go. The next one, reason I want to do one more is just to be careful when you're choosing these graphs. You don't need to look at anything else. There's not a trick. It's just being careful. Okay, so we want to look at the domain or the vertical asymptote or both. And we want to look at whether it's increasing or decreasing. All right, for this one here, what's very important about the domain, that's why I wanted to do this one. This -4 is on the outside. You only set the inside greater than 0. Right, do not do anything with that -4. Right, what the -4 does is it shifts the graph up and down. It's going to shift it down 4. That's actually not that super important. When you might be able to tell which one shifted down 4, but when it comes to log graphs, shifting up and down isn't the most important thing to worry about. Right, so we got the domain is greater than 0. If you want to write the vertical asymptote, it's x equals 0. And you can see from these pictures, x equals 0 is the y-axis. Both of these have the wrong vertical asymptote on the right side. This is at -4, this is at -4. And then the two on the left, they both have the correct vertical asymptote right on the y-axis, x equals 0. So we go to our last thing. Should this be increasing or decreasing? The base is 6, which is bigger than 1. It should be increasing. And which of these two graphs is increasing? The one up here on the top left. All right, so the one on the top left meets both of the standards, and it's the only one that does. So this is the correct one. The one on the bottom left, it's decreasing. As we go to the right, it moves down. Oops, didn't want to start boxing that in. Decreasing is not what we're looking for here. All right, so that's all the problems. Like I said, I did want to just graph one in the calculator just so you can see, especially with these graphs, you can tell that the graphs flatten out significantly. Now you kind of think about what this one here is. This right here, the y value is 0, that 1. sorry, the y value is 1 at x equals 1. And over here, the x value is 10. It's not even to 1.5. It looks like it's going to flatten out. Right, so what I'm going to do is just graph y equals ln or log of x. If you hit the standard graph, it's going to look pretty much like one of those that we talked about. It even has trouble with the vertical asymptote, as you can see here. If you type in big numbers, so as we go to the right, what I was saying before is this should go up forever. It should go up to infinity. Yeah, you can't type in negative numbers or 0 into logs. So if I type in 10, we get 1. If I type in 100, we get 2. If I type in 1,000, we get 3. And the way log base 10 works is every 0 after a 1 gives you one more number. So even though it goes up very slowly, if I type 1 with like 15 zeros after or something, I guess I just did 16, the y value is 16. Right, now 1 with 16 zeros after is a very, very big number, but the point is it keeps going up. So if I could, in theory, type in 1 with infinitely many zeros after it, yeah, if I could just keep clicking the 0 forever, then the y value would go up to infinity. So it does go up to infinity, it just does it very, very slowly. Not many things in nature work like logarithmic graphs. If you plot points, but there is a lot of things in chemistry that you use logs to help yourself understand. One of the questions that's pretty common is dealing with the pH of a chemical. Its equation has a log in it. But that is log graphs, section 4.4.